Nice to see you all here this evening. So tonight we have a joint ACM Chicago and IEEE Chicago, along with the student chapters of ACM UIC as well as IEEE UIC. So my name is Alvin Chin. I'm the chair for the ACM Chicago chapter. I'm also the chair for the IEEE Computer Society Chicago chapter, as well as the co-chair for the IEEE Chicago. We have a quantum computing local group. So we're all working together to do this particular talk this evening. And so we're very pleased to have Professor Lane Gunderman from the EC department at UIC that will be talking about what makes quantum computers different, what they enable, and how to build. Like I said, I'm the chair for the ACM Chicago chapter. How many people here know what ACM is? What does ACM stand for? Association for Computing Machinery, right? So if you don't know ACM, everybody heard about the Turing Award? That's something that is given by the ACM. We have Payam, who's our vice chair, our treasurer here, Greg, who's doing the video camera, and we have our communications chair, Henrietta, who couldn't come this evening. We have our Meetup website, so you can go there, but we also have Facebook, LinkedIn, and X as well, if anybody still uses X these days. Yes, well, we have the ACM UIC student chapter, so maybe you can just say a few words.
Yeah, just quick a summary. We're one of the oldest student orgs on campus here and one of the biggest for CS. We have a bunch of different SIGs, so just like National ACM, who do a bunch of semester-long projects, and there's about 15 in total. They go from game development to normal math projects to iOS development, a bunch. We also hold trivia nights, LAN parties, and a bunch of random professional speakers. This is one of the game jams we had last semester. I thought it was pretty fun. But yeah, if you're interested, check us out. We're over in the normal CS building with all the other CS orgs in that one little alcove.
Cool. Okay, great. Thank you very much. That's the ACM UIC student chapter. And then, now my IEEE. All right, so now, IEEE Computer Society. Okay, so I'm the chair for IEEE Computer Society, Chicago chapter. We have our vice chair, Rajarshi Roy, who couldn't make it. We have our treasurer, John Waltz, and secretary, Dan Waterloo, right there. So thank you, Dan, for coming. And we also have our YP chair, Anurendra Venkatasan. So we're also, we have our X, our LinkedIn, and our Facebook too as well. We do a lot of events joint with ACM Chicago because, well, the topics are very similar. They're all about computing. So we like doing these joint events together. All right. And then, of course, the Chicago Quantum Computing Local Group. So we started this local group around like last year or so. The chair of this is Bizwan. Bizwan, are you online? Is he there? Okay, I don't know messaging there. But anyway, so I'm the co-chair of this quantum computing local group. And so the thing that what we want to do here is that, you know, IEEE is the largest, world's professional, largest engineering organization. And so the thing is that IEEE has a lot of stuff they do with quantum. So every year in September, they do something called Quantum Week. And so what we want to do is that, because, you know, Chicago is the quantum hub, so we want to do also a quantum computing local group to gather, you know, quantum computing folks together. So this is our first particular kind of event, and we'll be doing, you know, more of these in the future too as well. If you want to know more information, you can also contact myself here. So that's my alvin.chin@ieee.org. Okay. And what else do we have? Yeah. So I said special thanks to the ACM UIC student chapter, the IEEE UIC student branch. Do you guys want to talk about yourself or? So we need to thank them because this is their space. So we got to thank them for that.
So this is technically not our space. We rented this.
Okay. It's your space tonight, okay? So just go with that. Just go with that. Just go with that.
So we're the IEEE student branch. So we have students come in, we teach them technical skills through workshops. We also do various projects such as RoboSub, which is a competition in California. And we also have another project called ScrapBot, which essentially students come in, they work on different parts of the robot, drivetrain, electronics, programming, etc., and they hone their skills that way. And yeah, that's kind of the gist of our branch.
Okay.
Thank you guys for showing
All
up.
right then, thank you. All right. Then of course the Chicago section. So I used to be the past chair. I'm now the advisory chair for the Chicago section. So IEEE has many different sections around the world, and so we have a Chicago section. Fun fact: we are actually the second oldest IEEE section in the world, after New York.
Okay, thank you.
Yeah. So there you go. And IEEE Chicago was actually there during the World's Fair, so we have a connection to that. Okay, so enough about me. I'm not the person talking tonight, so I'm going to introduce Professor Lane Gunderman. He's from Electrical and Computer Engineering, and I think you actually used to work at University of Waterloo, correct?
No, I did my PhD.
Oh, you did a PhD there. Okay.
Yes.
Okay, in quantum computing, right? In
Yep.
their quantum Institute for Quantum Computing, right?
Yep.
Yeah, interesting because fun fact, I also went to University of Waterloo.
Oh, really? Nice.
Yeah, I did my undergrad and master's there, so in ECE. So anyway, we got this Waterloo connection there. Yeah, so he's going to be talking about quantum computers, what makes them different, what they enable, and how they build. So what's going to happen here is that we're going to have this particular talk. Oh, all right. Hi, Bishwan, do you want to talk about the quantum computing local group?
Yeah, I don't have the link actually to join. I'm struggling a little.
Okay, don't worry about it. It's okay. I already talked about it already, so don't worry about it.
Okay.
Okay.
Sure.
All right. Sorry. Technology. Hey, that's what makes it fun, right? I mean, it's too boring, right? Okay. Yeah. So so now we have Professor Lane Gunderman to talk about, and then we will have a Q&A. I think we'll give you about maybe until like maybe 6:45 or so. Is that good enough?
Yep, 40 minutes or so.
Yeah. Okay. And then after that, there will be.
I might need 40 minutes.
Okay, that's fine.
32, yeah.
No worries. And then we'll have a Q&A, so if you have any questions for Lane, do so. And as well, for those people that are online, if you have questions for Lane, you can also put them into the chat too as well, and we'll take them as we go. All right, and with that, I'm going to present Professor Lane Gunderman.
Thank you.
Now, I think that can they see your
It looks like the screen is distorted and some of the slides is over the.
Are you on the Zoom? Yeah.
Yes, it looks like and now I think it's getting better.
Yeah. So he is sharing his screen. So can you
Well, I need
enable?
to stop sharing, and then
Oh, okay.
I will share this one.
All right then. So how many engineers does it take to actually get this working?
Okay. Is it visible for people?
You can probably minimize that. Yeah.
There we go.
Cool.
Just one more share.
Okay, so, as mentioned, my name is Lane Gunderman. I'm an assistant professor here in the ECE department, and my overall goal from the talk today is that you'll be able to give a loose answer to these 4 questions. The first one is, what makes quantum computers different from the normal classical computers that we have in our cell phones and in our laptops? Secondly, once we understand what truly makes quantum computers different from classical computers, what could we possibly solve faster with a quantum computer than we're able to solve with a classical computer? Once we have that under our belt, we're going to talk about different ways that we might try to build a quantum computer, and then round out with somewhat natural question of, if there's all these things we could do with it, and we know how to build it, why haven't we yet? What's getting in the way? So, firstly, what makes quantum computers different than classical computers? So, most of our classical computers work with binary values, so it digitizes it into zeros and ones, and the reason we do this is so that they're robust against voltage changes. So maybe a 0 is 0 volts and a 1 is 5 volts. Then if you have a fluctuation of a volt, who cares? It still rounds out to the correct value. Now, if you've digitized your signal, then you can accomplish every possible binary operation using a bunch of and, ors, and not operations strung together. These form a universal classical gate set. Now, we've changed it from a continuous signal into a digital signal of 0 and 1 to make it a little more robust. In principle, you could instead use analog computing, where the actual voltage takes values between 0 and 1, and every possible real value represents a different number, in effect, in your computer. And by doing that, you're kind of upgrading your information that you're computing with from binary bits into different frequencies of waves. Now, we could apply the same sort of logical gates of an AND operation, an or a not, on these different oscillatory waves, and do computation that way. The reason why I'm bringing this up is that one of the common folklores for what makes quantum computers so much faster and more powerful than classical computers is this idea of being able to do tons of inputs all at the same time, simultaneously do your computation. But if we use analog information and waves as our communication format, we could also have this parallel computation. So it's not really on its own a signature of a quantum computer. As a simple example, we can consider just Wi-Fi. Everyone in this room is able to access the internet at the same time. This is because the Wi-Fi router is sending out different frequency bands that each person gets to communicate with, and it interleaves them in time. But the main point is that, in principle, this parallelism is not really a quantum feature that enables more powerful computations. Okay, then, if that's not really the source of the power, one thing that we may look at is, okay, well, what really makes quantum mechanics different from classical mechanics and regular physics that we're used to? One of the key signatures of quantum mechanics is a non-commuting nature. What this means is that the order of certain operations can deeply impact what sort of results you get. So one of the simple examples would be, say, measuring the position of an electron and then measuring its momentum. That ends up generally being very different than measuring the momentum and then the position. And in effect, that says the order of operations are non-commuting, so you get something different based on which order you do them. Now, while this is a key signature of a quantum mechanical system, this isn't actually anything truly quantum mechanical. In that, if you think about daily life, the order you put on different shirts, for instance, very much matters. So if you put on a dress shirt and then a t-shirt, it looks very different than a t-shirt than a dress shirt. Or, even stepping further back, we can think of it geometrically. So on the right, I have kind of a diagram that will show a non-commuting set of operations. These are rotating by 90 degrees clockwise and reflecting across a diagonal line. So if we start at the top and go down the left path, if we rotate first and then reflect, the red dot is in the bottom left corner. But if we instead had reflected and then did our rotation, the red dot is in the upper right corner. These are manifestly very different locations for the red dot to end up in. But I haven't said anything about information, quantum mechanics, or anything like that. It's just something that happens in nature. So that's not really the source of the quantum computational advantage. There's something a bit weirder that really gives the advantage, and that is primarily this tool called entanglement. So the short version is that it allows two quantum bits, or qubits, to be interacting with each other in a very deep way and correlated more strongly than classical information would allow. So this level of correlation means that if we do some operation or measure the first qubit, say qubit A in this diagram here, it will do something very different to qubit B based on what we got out. So this expression here, so ignore the 1 over root 2. That doesn't matter for physical interpretation. But what this says is that when qubit A is to state 0, then qubit B will be in the state 0. And at the same time, if the qubit A is 1, then qubit B will be 1. So if we measure a 0 from the first qubit, automatically it forces the other qubit to become 0. This is something very unusual in that measuring something can have an impact on a totally different location than we were actually messing with. And it's this entanglement that will enable all of our faster quantum computations. But if this entanglement is where the magic really comes from, it would be kind of goofy if in order to generate this entanglement, it took solving an incredibly hard problem. So in theoretical computer science language, if it took solving an NP hard problem to generate this entanglement, we wouldn't really get any sort of advantage. So how hard is it to make this resource of entanglement? So the short answer is actually surprisingly easy. Back in the 60s, Hartman and Hahn came up with a scheme that, once you go through modern language changes, generates entanglement in NMR devices. And this is 60 years ago. Molmer and Sorensen came up with a technique for trapped ions where you can generate entanglement surprisingly easily. And then beam splitters for optical or light-based computing have always done entanglement generation in effect. But only in 2001 or so was it recognized that that's a resource that we could actually use when doing our computations. So the point here is that entanglement gives us this ultimate power, but it's also really easy to make in general. So now that we have an idea of what really makes quantum computing different than classical computing, let's move toward what we can do with this now. So what tasks could we solve with a quantum computer faster than a classical computer? So these are going to kind of have themes among them. The first one is secure communications. So classically, things like RSA encryption is secure up to an exponentially hard problem to solve. But for certain quantum protocols, you can make it so that it is secure up to our understanding of quantum mechanics. That if someone tried to eavesdrop on the information, their obtaining of information that's being transmitted on its own will make it so that you know that someone was trying to hack the information, and it no longer can be decrypted anymore. So some instances of this that maybe you have heard about is quantum key distribution, or QKD. There's quantum position verification, which basically says if someone is intercepting between two parties communicating, it's going to basically take longer than the speed of light for the person to observe the information. So if someone intercepts, you know that someone has intercepted the message. And then more broadly, this sort of concept is worked on in quantum information theory. Now, that's one problem that we could solve. Another one are algorithms centered around tests of quantumness. So one category are what's known as non-local games. They're mostly a mathematical tool, but they basically are ways to get signatures that for sure some party is actually using a quantum computer. So classically, there's this famous game called the CHSH game, which has a 3/4 chance of winning, but if you are allowed a quantum computer, it goes up to about 83%. So if a party is getting above 75% after playing the game a lot of times, you can assume they truly have access to a quantum computer. Beyond that, there have been recent experiments where people have used this, used quantum computers as certifiable random number generators. Now, for most of our day-to-day life, the ways that we're generating random numbers already are good enough. But if you were, say, a massive hedge fund, and you wanted to make sure that no one was actually cheating the random number generation, this protocol would in principle give you, up to our understanding of physics, a guarantee that the numbers being generated are truly actually random. Okay, other things we can do with this entanglement more directly is a protocol called superdense coding, and in this case, you and another party share a pair of entangled qubits. You go away, you do something to it privately on your own, and just send the qubit back to the other party. Surprisingly, when the other party does a measurement, they can actually receive 2 classical bits from you, from a single quantum bit being transported back to you. Beyond that, it also is protected against an eavesdropper looking at the information, because that will destroy your entanglement in your system. There's also a technique called state teleportation, which utilizes entanglement. So the diagram in the bottom is in a circuit what is going on, where the bottom two, when we have that O with a plus in it and the dot line below it, that indicates entanglement is being generated. So you entangle a pair of qubits, then you entangle it with some state that you're trying to move from one location to another, and by doing a certain measurement protocol, you can teleport the information in your first qubit to the third qubit. An important caveat there is that you are not actually moving the qubit, you are just copying the information or moving the information from one qubit to another qubit. So, for instance, that means you can't teleport objects. All that you can do is move the information contained in the object to another location. It's a subtle but important difference. And you can extend that idea to do what's known as gate teleportation, where if you have a really complicated task that you want to perform on your ongoing computation, you can offload it to some extra qubits that you just have prepared, and then at a later time, by doing a certain measurement protocol, you can effectively apply that operation that's really hard to do with a far simpler, or a bit simpler of an operation, which is useful for making more robust quantum computers. But it's kind of this different mathematical protocols that you go through that let you move information around and perform operations that classically would be impossible to do. Another sort of task where we have a big improvement for a quantum computer is if we have a bunch of unsorted, unstructured values in a database, and we're looking for specially marked items, and let's say there are K of them. Classically, to find those specially marked items, we have to go through the whole list until we find them. But with a quantum computer, assuming you have access to a certain operation, you can make it so you only have to look at roughly the square root of the number of items in the list before you find one of these specially marked items. Now, that problem itself is somewhat contrived, but the same protocol can be extended from, this is known as Grover's search, to the more general amplitude amplification protocol. So if you see especially an applications-focused quantum algorithm paper or research result, in all likelihood, they're doing an amplitude amplification result where they're getting a quadratic improvement. So if you see a quadratic improvement, it's probably this technique. Okay, besides that, there's probably the most infamous quantum algorithm, Shor's algorithm, which in effect allows you to factor composite numbers, which is at the heart of RSA encryption for our current internet security. Now, well, you may think, okay, we don't have a quantum computer now, so the internet is safe. This actually leaves us vulnerable to, right now, a save now, decrypt later security attack, where they say download an entire email server. They can't decrypt it now because it's really hard to do with the classical computer. But the moment they get a quantum computer, they can decrypt all those messages and know what they say. So, because of that, places like NIST have put out new post-quantum cryptographic protocols that are widely believed to be secure, well, one, against classical computers, but two, even against quantum computers. And if you update, how your internet security is being handled, in principle, you'll still be safe, until we come up with something beyond quantum computing. Okay, beyond that, the most important, in my opinion, use for quantum computers would be simulating physical systems. Broadly, this is called Hamiltonian simulation. And for these sort of problems, we're looking at how a system changes over time, how it folds, how it, different energy values look like in terms of the structure of the system. And some examples of this would be material science discovery, drug discovery, protein folding, simulation of high energy and mid-scale physics models. So on the right, in the top right, we have the Fenner-Matthews-Olsen complex, which is really important for photosynthesis. While on the bottom right, we have what's known as Kitaev's honeycomb model, which is believed to have big impacts for high energy physics. currently, most supercomputers are being used for these sort of simulations. So if a quantum computer can, be built, ideally they'd be able to handle these problems a lot quicker than current computers, and we could save a lot of resources. Now, on the flip side, we have to also confront the reality that AI has made incredible progress on some of those problems. So AlphaFold, it was in effect awarded the Nobel Prize in Chemistry 2 years ago for basically being able to predict protein folding incredibly accurately and efficiently. Now, the caveat there is that it's trained on huge amounts of data. We have been studying protein folding since the 70s with computers. So we've got, terabytes of data that it can train on. But for things like, catalysts in drug discovery, we have a lot less data for it to train on. So I would say that's one avenue where quantum computers still have some value. Beyond that, AI is a heuristic solution to these problems, while quantum computing is, if it were implementing these techniques, would be based off of our understanding of fundamental physics properties, and we could simulate it up to our understanding of quantum mechanics. So, who knows in time if AI would get rid of the main use of quantum computing, but I would bet that it would need to go more hand in hand together. Lastly, there's one other set of algorithms that I want to briefly talk about, one of which is solving a set of linear equations. It's more of a math topic, but there's a quantum algorithm that solves it exponentially quicker. With the catch that the moment you start looking at the output, you lose any advantage. Because, yes, it solves it exponentially quicker, but the size of the output is exponentially big. So, there's proposals for still using this technique as a subroutine, but we don't know for sure if it's actually helpful. Another task is in big data, when you're looking at large amounts of information, you're generally curious about what are the dominant trends and how dominant are those trends. A typical tool for analyzing this is what's known as principal component analysis. If you've taken linear algebra, these would be like your singular values and singular vectors. There's a proposal, or a number of proposals, for a quantum algorithm to do principal component analysis, but I will also hedge that they tend to require somewhat dubious resources. They assume you can do certain things that might not be realistic to assume a device could ever be able to do. Okay, so that's the end of what a quantum computer might enable us to do. Let's now talk about how we might actually build a quantum computer. There's a bunch of different ways that people are trying. But before that, let's talk very briefly about ways that quantum mechanics and quantum technologies already impact our lives. So lasers are purely quantum mechanical in their nature. X-rays, MRI machines, if you've broken something or needed something examined. Transistors end up using a quantum mechanical feature. In the bottom middle is atomic clocks, which lay people mostly don't need to care about. But if you want incredibly precise measurements of time, you need to realistically use an atomic clock. And the hope would be that quantum computers would occupy, one of these spots where any quantum computer is basically going to build off of almost all of these technologies. So the first attempt at making a quantum computer were with NMR, or nuclear magnetic resonance devices. These are basically MRI machines, but you take out the person, but keep the liquid they injected you with. So they perform kind of like an MRI scan on sets of molecules. And using a strong magnetic field, they orient the intrinsic spin of these different ions, or sorry, not ions, isotopes, and then you apply radio frequency pulses to do your actual operations. Now, the advantage of an NMR quantum computer is that the qubits you generate are extremely high quality. Like, their lifetimes are on the order of hours or days, and many other platforms we're looking at microseconds. So that's great. The downside is, from a theoretical physics standpoint, they can be explained by a local hidden variable theory, basically meaning they're not definitively fully a quantum mechanical system. Further, how are you going to communicate between different NMR devices? These are big machines, maybe 5 feet tall and 3 or 4 feet in diameter, and they have liquid helium temperature inside of them. How are you going to hook up multiple of these to have a secure communication protocol? Beyond that, you also would need extremely fine resolution of frequencies if you wanted 100 qubits even. So, for those sort of reasons, NMR quantum computers fell out of the favor for actually building a quantum computer, but they're still useful as proof of concept devices. The generally most popular approach are the superconducting systems. So all the way on the right, we have what's colloquially called the chandelier model of a quantum computer, and between each of the gold plates, there's a massive temperature drop. So on the outermost layer, it might be liquid nitrogen around 77 Kelvin. The next layer down, maybe liquid helium at 4 Kelvin. Next layer down, pumped helium at, I think it's 2.4 Kelvin. And you keep going down until you're in the tens of millikelvin range. And at the bottom layer is where you'd actually put your quantum computer. And it would look like the picture slightly to the left, where each one of the little clothespins, or hairpins, on this is 1 qubit. So you've got something 8 feet tall, and at the end of the day, your actual device is maybe the size of your pinky nail. Now, the downside here is that naturally, if you want this at liquid helium temperature, you need to keep it at liquid helium temperature. That's really expensive and really hard to maintain. Besides that, for these sort of qubits, you can only do interactions between nearest neighbor qubits. So if you want to interact 2 far away qubits, you have to swap their information down the line, get them close, do your operation, and swap back out. This being said, currently they're the best approach we have. And this is the approach being taken by Google and IBM and a lot of other companies. And it's what the Nobel Prize in Physics was given for this past year. Another approach are these neutral atoms, where you arrange a bunch of individual atoms into some sort of lattice with lasers, and then, assuming you keep the environment around them at an extremely high vacuum, meaning very low pressure, your atoms will stay roughly in place. You can do laser pulses to do your operations. Now, one of the really nice things about this is that you can actually move your qubits around in space. So if you want to interact far away atoms, instead of having to swap the information over, you can just drag them next to each other and do your operation. Now, 4 years ago or so, this was basically considered a dead approach that wouldn't work, but in the past few years, it's had such tremendous progress that it's only a little bit behind superconducting devices, which is pretty remarkable. Then, my personal favorite approach are these photonic implementations, so different ways of using light. And one of the main advantages here is that we get to use the past 60 years of people obsessing over making higher and higher quality optical components. So we've got amazing mirrors, beam splitters, lasers, fiber optics, photon counting systems. Now there's a number of ways to implement this. There's what's called a GKP encoding, a dual rail encoding, a KLM. There's a lot of different ways to try to make a photonic quantum computer. None of them have fully worked yet, but if they were to be made to actually work, one of the big selling points is that these devices, almost all of it, operates at standard temperature and pressure. So you could have 98% of the device running in this room, and then you need a little bit that's, say, at liquid helium temperature. So for instance, at Xanadu, they need to do individual photon number resolution. That requires an incredibly cold environment. But all the rest of it can be done on the tabletop, which is pretty appealing. Now, beyond that, just as a speed round, we've got trapped ions, where you're using electromagnetic fields to couple individual ions together. There are spin defects, where you have, say, a nitrogen vacancy in diamond, or you have quantum dots, and these generate your qubits. There's the very theoretically appealing approach of Majorana fermions, where in principle they're amazing because they inherently do what's called topological quantum computation. The catch is, even still, no one has an uncontested Majorana fermion. In that, for the past 10, 20 years, roughly every 6 months, some researcher or group will say, we've made one. And then 3 months later, other scientists will say, no you didn't, these other things explain it. So even right now, Microsoft's claim is not yet contested, is the best way I can put it. There's a real chance that in a couple months, someone will say, no, you didn't even make one. Now, the reason I went through all these different modalities is that there's really no winner at this time. There's a loser, NMR is definitely a loser, but there's a lot of possible winners. And I would say there's reason to believe that even in the end, we won't want just one approach. So let's say photonic works. That's wonderful because it has all these temperature and pressure advantages, but there is a question of how are you going to store your information? Are you just going to have your light representing your information running around in a loop for weeks on end? Fiber optic cables are great, but they're not literally perfect. So I would say there's good reason to believe we'll probably need at least 2 of these platforms to work together to really make a full-scale quantum computer that can do the stuff we talked about. Okay, and then briefly back to Alvin's point, we've somewhat recently broken ground for the IQMP, Illinois Quantum Microelectronics Park, at the old Steelworks on 87th, I believe. And part of that park will be for the National Quantum Algorithm Center that is planned there. There are a number of companies that are saying at least that they plan to move in there, so that hopefully will be a big boost to the Chicago quantum effort. Okay, so we've talked about what makes a quantum computer different. We've talked about what it could do. We've talked about how we might build one. Now we get to why haven't we? As you may expect, it's because of noise. We're dealing with, in some cases, individual atoms. Of course, small fluctuations in the temperature or pressure or voltage in your system could radically destroy your information. You're going to have garbage compared to what you expected. And no matter how hard we try, we're never going to really avoid this problem. Our best bet is to just try to correct mistakes quicker than they're accumulating on their own. Now, this may at first seem like a purely quantum computer problem, but classically we already kind of had this problem. So for Wi-Fi, for instance, we've gone through different stages. I think everyone in this room has lived through 3G Wi-Fi on your phone, 3G LTE, 4G, and now we're getting 5G. It's solving that same sort of problem where you're trying to pack more and more information in and still keep it robust to some amount of fluctuations in different parameters. Now, unfortunately for quantum computers, we haven't even reached the point where we're able to keep information. Google in the past year said that if they scaled up their device, they would expect to be able to preserve the information. What they've done so far is said, we can slow down how quickly it's destroyed. So we still need to reach a point where information can be kept. And then we have another hurdle of, okay, the information is kept. Can we keep it and do anything to it, any sort of operation to it? And we're probably a couple years away from reaching that milestone, much less having a full-scale device that would be protected against random fluctuations. So for the next few minutes, I want to give you a little insight into how we solve this problem classically and how we might solve it in a quantum computer. So very, very briefly, for a classical error-correcting code, I like to think of this as kind of a little bit of a story where you have 2 people, you're both in lighthouses, and it's a foggy night, but you want to still communicate. We'll pretend it's the 1800s or 1700s, so there's no phones. All you have at your disposal are a pair of stencils or placards that are square cutouts and circle cutouts, and you can hold them up, but because it's a foggy night, sometimes the other person will misread which symbol you actually held up. So how can we start allowing them to sometimes misread? The simplest approach is to just hold up the same shape 3 times. If they misread it 1 time, who cares? They'll say, okay, I saw 2 squares in a circle. They probably held up 3 squares and I just misread one. What if we want them to be able to make 2 mistakes? Then you repeat it 5 times of holding it up. 2 times of making a mistake, you just take majority vote. You know what message was meant to be said. Now, you can keep doing this longer and longer, but your arms are going to get sore, and it's a lot of time to have to keep holding things up. So what we'd like to do is come up with more efficient ways of communicating information. So this is one way that we might do it. We would pick messages so that if we took the product of this block of numbers with that message, we would get out a 0 set of numbers. This is what's known as a Hamming code, and what it does is it says for every 7 times you hold up a placard, you're going to communicate 4 pieces of information, and 1 mistake can still be made. So if we compare this with our first approach of holding up 3 times, 1 out of every 3 placards we've held up actually communicated a piece of information. But by doing this Hamming way, 4 out of 7 are communicating information. So more than half the time we're holding up a placard, in effect it's communicating a piece of information. Now, you can go wild with this and make it a really difficult and general problem. The main point is that over the past 30 years, we've come up with ways to make, in effect, the best ways of representing messages by holding up these placards, where a constant fraction of the time we're holding up a placard, some new piece of information is being conveyed, and the other party can miss a constant fraction of the message and still figure out exactly what was being sent. Now then, how would we do this on a quantum computer? Well, let's copy the main idea. Let's just repeat information. If a message gets misread, we just take majority vote. Now, if only life were that easy. There are 2 things that get in the way here. The first one is if you measure your quantum information while you're still doing computations, it becomes a classical computer. So you can't actually measure to see if an error has happened. Okay, well if you can't measure, maybe we can make a copy of it and then measure that. Turns out there's this other result called the no cloning theorem that says you can't make a copy, measure it, and then correct the original. You only have 1 copy of your information in general. So how are we going to get around these? It turns out you can play this kind of cheeky game where instead of actually asking for the information, what you do instead is ask whether adjacent qubit values agree or disagree. Now this is a little bit weird in that we're not actually finding out what the information is. We're just asking about, do they agree or not? And based on that, we're going to infer whether a mistake has happened. So here on the right, these black dots along the horizontal lines indicate we're asking whether the values agree. And then, we ask at first, do the first 2 qubits agree in their value? Yes or no? Then we ask, do the second and third agree? Yes or no? And based on that, you can figure out exactly where a bit flip may have happened or some error. Now, you can go wild with this too, and I think 4 years ago was when we finally had the first proof of, in effect, the best possible ways of doing this protocol for quantum computers in a theoretical sense. Again, we don't actually have any success yet, so we'll see if in practice those ideas are really that helpful. Now, to indulge myself, I want to talk about going a little bit beyond qubits, where each of our computational registers stop having just 2 values, but now they have 3 or 5 different values that they could take. Now, there's a couple of motivations for this. Firstly, for certain isotopes or elements, like strontium-87, it naturally has 10 different values it can take. So if we only allow ourselves to use 2, we're throwing away 80% of the computational space. And since the computational space multiplies together, we're really kneecapping the size of problems that we can solve. So maybe we should actually take advantage of all the levels it has. Likewise, when we're talking about the different ways that noise may be impacting your system, it's kind of naive to just look at 2 of the different values and analyze how the noise impacts those, when we've got 8 others that we're just ignoring and hoping don't matter. So beyond that, there were some algorithmic advantages. So if we replace our registers, instead of being 2 levels or 2 values, to 7 values, we only need about 30% of the number of computational registers to solve the same problem. There's also a couple of foundational advantages. So Hudson's theorem basically tells you or a simple test for knowing that you truly have a quantum mechanical state. Then there's also results related to contextuality, which we didn't talk about, but is another source that some people point to as the advantage for quantum computers. Beyond that, there's actually better error modes, or different ways that errors can happen, scaling, than we would initially expect. So if we have 10 different levels of energies, we would expect very rarely for the energy to go all the way from the top to the bottom. That's a huge amount of energy you would be spitting out or randomly absorbing. What's more likely is it goes from the top to the second to the top. And then from there, maybe it will go back up, maybe it will go back down. But instead of there being roughly Q squared, many ways that noise may happen, for a lot of systems it's more like Q, which is quadratically better than at first we would expect. And if we went really extreme with this concept, we get this paper from the last year called Factoring an Integer, so that's Shor's algorithm, with 3 oscillators and 1 qubit. So you can basically turn it from needing tens or thousands of qubits into just needing 4 computational spaces, and you can do the breaking of RSA. Now there's a major caveat here where these are mathematicians, they don't care about the reality parts at all, and the protocol is very non-physical. But mathematically you could solve that problem with just 4 registers or locations for doing the computation. And the bulk of my research is in designing or carrying over schemes for protecting the qubit information into these more exotic cases, so that maybe we need only smaller devices, and sometimes you get really weird and novel properties in your ways of protecting the information. So, to just kind of conclude, quantum computers gain their real power from entanglement, not from this parallelism that's sometimes discussed, nor is it purely from a non-commuting nature. What it could enable is destroying RSA encryption. It could allow us to discover new medicines and materials way quicker than before, and it could allow really secure communication between different parties. Something that it can't do is make every hard computational problem easy. So I believe, for instance, if you had the traveling salesman problem, and if you're familiar with that, I don't think there's a quantum algorithm that makes it easy. It's still a really hard problem for it. So, those are the different things it could and can't do. Other things that we discussed were different ways that we might implement a quantum computer, and that we haven't done it yet because we're fighting against noise, and that's realistically the big challenge we're fighting over the next 5 to 8 years. All right, and that is the end of my talk. Thank you for listening.
Great, thank you. Yeah, okay, so we got time for some questions, so maybe we'll start in the room there, and then we'll go to the online. So maybe we'll start, Greg.
Okay. One of the quantum properties is this entanglement. My understanding is you can have like 2 atoms entangled, separate them a great distance, and communicate via that way. Why then, in the quantum computer, do they have to be so close to each other, and I've got to flip-flop back and forth? Why do I I seem like I lose that property?
You still get mathematically the same property, but you're right that you're not really using it to communicate anymore. Instead, you can use it to deeply impact some other qubits by performing operations on other nearby qubits. So yes, to some extent you lose some of the specialness, but at the same time, it's what really makes a quantum computer different. Does that mostly answer, or you're welcome to ask follow-ups, please.
Yeah, one in the back.
Thank you. Besides destroying encryption, what are some other ways an organization can use a computer in a malicious way?
You know what? I don't think.
Online.
Oh, sorry. I don't know if there's a full answer to that, of what else you could use a quantum computer for in a malicious way. One of the, I guess, tangentially related things is where you pretend you're doing something different than you truly are. So let's say NIST has a quantum computer, and you want to use it to break RSA encryption, but their rules say you can't do that. So what you could do instead is pretend you're doing a Hamiltonian simulation problem, but it's really breaking encryption. But from, if you're not really digging into the program, you don't notice that the person's lying. Beyond that, I don't know what other malicious intents there might be. And for me, I prefer to keep my naivety and be like, oh, it's only for good.
That's the follow-up.
Yeah.
It can discover new medicines. Can it create possible viruses or diseases?
It could. Yes, sorry, in that, unfortunately, one of the big benchmarks in Hamiltonian simulation papers was a new plan for explosives. Which to me, I'm like, okay, could we have focused on something neutral or good first? But yes, it could be used for those purposes.
So let's take maybe one question from online. IM, is there a question from online?
Yes, Gabriel asks, what does or will quantum programming look like?
I would say to some extent we don't really know what the future quantum programming languages would look like, in that currently it's just basically specifying a bunch of matrix operations, and that outlines what your quantum computer would do. In all likelihood, it would start being, instead of matrix operations, it would be blocks of operations, kind of following like in classical computing when we had, what is it, assembly, where you had to actually like tell registers where to add what to whom. And now we just say, add this number and keep it somewhere, I don't care where. So I would say in the future, quantum computing might look a little more like that, where we're not as concerned about what the actual device is under the hood, but we don't fully know.
So what about then, follow-up, what about IBM Qiskit?
That is an approach.
Okay.
So in that, at the end of the day, for most of Qiskit, you're basically still specifying what matrices you want to apply with.
Okay.
A follow-up question on
Yep,
this.
go ahead.
Given that large language model training is dominated by larger scale linear algebra and optimization, do you see any realistic path where quantum linear system algorithms could impact the AI training, or are there data loading and the noise constraints that you mentioned are too severe?
I would say it's possible. Oh, sorry. Basically, how could quantum computers maybe help with LLM trainings? So it's possible it could help, but I would say at the moment, until we figure out how to use like those solving of systems of equations without that exponential overhead of looking at things, we don't know if it will help. There are people who are promising it will, but using dubious resources. So they're assuming, for instance, no matter how big of a piece of data is that you're trying to call from memory, it takes the same amount of time, which seems a little questionable, that if you had something a terabyte, it would take the same time as 5 bytes. We'll see how it shakes out in the end.
I think there's a question there.
Yes. Thank you so much, for this presentation. This was great. Quick question: why photonic qubit, is your favorite one? Is it just because of saving on cooling, or there are different responses to this question? And also, how far do you think we are from any practical, implementation?
So, to repeat the question, why do I like photonics so much, and how far are we from any practical implementations or problem solving? So, part of why I like photonic best is because it was the first job I had out of grad school. But also, it seems really appealing, and physicists have spent, I guess, about a century now focusing on quantum optics as one of the main directions. So we understand it very well, and it seems like a good approach. But for all, I want to say, photonic approaches, they have a really hard uphill battle, where making their first 10 qubits, let's say, is incredibly hard. Then once they've made 10, it's trivial to go to basically infinite, or, really, really big scale. Because we have all these high quality mirrors and stuff already laying around. But for the company I worked for, the real challenge is making their qubit in the first place, and they've only made a really, really crummy one. So in a couple years, maybe they'll hit a good break-even point, and then they'll take off. How far are we off from a practical quantum algorithm being implemented? I would say probably still a decade away. We have made much better progress than expected the past 5 years. So it could be shorter, but I would say 10 years is already being a little bit optimistic. In that, the first, motivation for making these devices was 30 years ago. So 10 years seems like a short time, but we will see.
Question? Yeah.
A follow-up question.
Go ahead.
Which application do you realistically think will deliver the first clear economic impact? Is it like cryptography, material simulation,
$1 billion question.
This was something I was discussing with someone before the talk. Shor's algorithm could have a huge impact. The catch is we have these post-quantum protocols, cryptographic protocols. So in some sense, being able to run it, the moment someone runs the first time, people are just going to stop using a protocol that's vulnerable to it. So it's kind of a useless protocol once it's implemented. So to me, I would say these different drug discoveries and materials insights are the more likely profitable direction that could happen.
There's a question in the chat, if you don't mind asking. Do you imagine having hybrid systems that combine quantum / classical computers?
Yes, I could foresee that, and even in Shor's algorithm, a fair part of the algorithm is actually a classical computation. That's pretty easy to do. You could do it on a quantum computer, but why, when classical computers are so good? But there's a particular step that requires a quantum computer. So I would expect some amount of, crosstalk and cross-computation to be required in the long term.
Okay, let's take it.
Yeah, so with the Shor's algorithm, how of course it has its classical, you could say, variant, and also the quantum implementation there.
Yeah.
When you're speaking about the error correction, kind of this idea of getting certain information about the underlying state of the system without necessarily revealing aspects of the system,
Yep.
is this kind of analogous? Like, would there be would these be kind of similar protocols to what we see from like zero knowledge protocols in the classical sense? Are we kind of converting those over when we're doing that?
I think your question is beyond my scope.
Okay.
So I'm sorry.
Yeah.
That sounds like a good question, but I can't answer it. I'm sorry.
Oh, maybe in the back there.
Not ever having read any papers on the subject, I always figured that the promise of quantum computing was in tunneling. There's a lower energy state on the valley on the other side of the mountain. The electron somehow goes to the valley on the other side of the mountain. So I figured that quantum computing was you set up the system so that after it solves the problem, it enters a lower energy state so that it somehow solves the problem. Now, am I completely wrong? I never heard I didn't hear anything from you today about tunneling.
So,
So just for online, the question was learning about quantum tunneling.
so I would say there's both two different parts to answer your question. On the one hand, physically, quantum tunneling is really important for transistors. Now, in terms of the computation and quantum computer side, that relates more closely to what's known as adiabatic quantum computing or quantum approximate optimization algorithms, where basically you start in a low energy state and very slowly change the rules that are dictating your system and hope that when you've made it a really hard problem that you've encoded into the energy structure, you're still in the ground state, and that's the solution to that problem. So yes, it can be a powerful tool, but I didn't talk about that. So yes, that is one direction that I partly neglected out of my own forgetting about it, but partly because it's also had some kind of negative results about it, saying that, for instance, one or two layers of quantum approximate optimization algorithm is classically easy, in that you don't actually get any quantum advantage until you get like a really deep and complex problem. So I didn't feel like highlighting that as much.
Anybody else? Okay.
Yeah, Caroline.
Professor, you mentioned that one of the biggest advantages of quantum is communications.
Yes.
My question is, does that require every single node in your network to be
It'll perform operations, which is kind of weird to say you can do a quantum computation without a quantum computer. I just need to have one.
So am I simulating on your machine, or?
You would be simulating it on your quantum state. You would not need a machine at all. I was like, you would need a machine to like measure the qubit value.
That's what Qiskit is doing, right? Like IBM?
I don't think so, but I could be wrong. I know Xanadu is taking that approach, but I can't comment on the other one offhand. Yeah.
Okay, question there.
Yes, quantum computer depends on qubit, classical computer depends on electrical bit.
Yep.
And so the more, then the number is higher of quantum bits, the more powerful the quantum computer will be.
Yes.
And it's like 7 or 9 years ago, Chinese Academy of Sciences, they developed like a 7 qubit on the computer. And, but I didn't think so, that's the highest one. But my question is that now almost 9 years passed, what's the latest development about the number of quantum bits?
Okay, so let me just repeat the question for those online. So the question regarding about what is the latest in terms of number of qubits?
Or no, it's the number of values that a qubit or a register may take. So technically speaking, light has infinitely many levels. That's not too helpful though. For what is it, trapped ions, I believe the record is maybe 19 right now by a group at the University of Waterloo. But
It's Canada, right?
Yeah.
Yeah, Canada, yeah.
So I think it's like 19 is the current record. For superconducting devices, I think people have only gone up to 3. But what is it? Strontium-87, I think someone has actually tried to experimentally make a very small quantum computer, and that has 10 levels. So I would say there's a bunch of different values for the record based on which way you're looking at it. But the true highest number is photonic because it's automatically infinite. But that's also cheating.
Are there any questions from online, Diane?
I can't say. I think that's it.
Okay, so then any more questions here in the audience?
Yes.
Okay, so with the with having qubits with multiple levels, how would this change the programming and algorithms? Does it actually make a difference on what gates we talk about and how those apply?
So when you go from beyond qubits to qubits or bosonic systems, how does the programming challenge and algorithm challenge change? Part of the answer is people have not looked into it enough. So we know what are a set of operations, that would be able to do every computation, even, at 11 levels or so on. The challenge is, how do we translate algorithms into those operations? That's something, to some extent, my research group is looking at. But we don't have a full answer, and naively, you get like a logarithmic improvement in the number of registers that you need. But a group, I guess, was it at UChicago, and now one of the leads is at Northwestern, found that they actually got more savings than they anticipated. That's the best I can answer. But it's especially if you're more into math, a kind of fun problem to try to solve.
Maybe a question to ask is that, I think I've heard like IBM mentioning about that if you want to do some really actual practical application of quantum computing, that you would need something but at least like maybe 100 qubits or something like that. What's your take on that?
I think that's accurate. Sorry, you'll need 100 logical qubits.
Logical qubits, right.
And you'll need something currently like, I forget if it's 10 million physical qubits. So we're a good while away from the first interesting algorithm implementation. But those numbers are mostly right. They're caveated in that the way they're protecting the information is, to people like me, incredibly wasteful. But it is the current leading approach. Other approaches, there was a recent report from a company saying 100,000 physical qubits is enough. We'll see what ends up happening. Yeah, sorry.
So I'm kind of curious, because you're working on photonics. Do you work with like one of the most advanced and most money spent in photonics has been with semiconductor manufacturing, because that's very precise control of lasers, and do you work with any of them?
I would say, unfortunately, to your question about which sort of companies to work with for photonic things, I basically just do math. So I have no experience in that. My math is guided by the physics mandates would be helpful. In terms of like different actual materials being used, I have no idea. As I was saying to someone beforehand, tungsten, selenium, or tin, selenium, they're about the same to me. Yeah, I don't know if those are the right materials, but no. So, yeah, I know so little about that I can't comment.
Okay, so I think we are already past 7 o'clock, so I'm going to just do some final things before we end here. So we got this already. So if you're interested, IEEE Chicago is a partner. Oops, I need to.
Oh, yeah, just yank it out and I'll also stop sharing.
Online can probably see, but you guys can't see.
There you go.
Okay, yeah, so what I wanted to say is that March the 3rd, 2020, March the 3rd, so it's coming Tuesday, there's a cybersecurity summit, and by the official cybersecurity summit, we actually partner, IEEE partners with them every year. So if you use this code CSS26-IEEE-CHI, you get complimentary free registration to get there. And it's at the Chicago Hyatt Regency over on the Upper Wacker. So that's the first thing to mention about. Yep, of course. Oops, sorry. Okay, that's the first thing, cybersecurity. Second about that, we have our next ACM Chicago talk, which will be actually a week from now, next Wednesday, March the 4th. So we're going to have David Giard, who's a partner solution architect at Microsoft, give a talk on effective data visualization. It's in person at the Aon Center, so if you know Aon Center, over near where the Millennium Park is. And also will be online on Zoom as well. That's the website for you to register. Also, IEEE, if you are, I see some students here, we have a student leadership conference competitions. So IEEE Chicago is part of Region 4, which is the Midwest. So we have 3 different competitions submissions are due March the 14th. So you students here, if you have, a teams, you can do a paper competition. You can also do an ethics competition. where we give you an example situation, and then you gotta apply the code of ethics. And then we also have a Shark Tank pitch competition. So if you have a startup idea or technical project or early stage startup idea, you can also submit to as well. So you can just go to the nexus.art4.ieee.org/competitions. And the actual event will be held on Saturday, April the 11th, and it will be at the IIT Kent School of Law. And of course, upcoming speakers. So we're always looking for speakers for our events. So if you have some interesting research or some interesting work that you want to talk about, you can contact Vice Chair at chicagoacm.org, Chair at chicagoacm.org, or myself, alvin.chin at IEEE.org. So thank you everyone for coming this evening. Those people, thank you for coming online too as well. I think there was a comment on the chat regarding, but is this recording being going to be put on? Once we have the recording in its process, we will make it available on the ACM Chicago YouTube channel. So wait for that. There we go. Thank you, AI. Yeah, thank you guys.